Okay, so as promised, here's a video for the first part of the 9-1 notes. So we're only going to do about a section or two in chapter 9, and just to kind of tie in some ideas with the waves and things that we've done recently. So a couple ideas that build off of that a little bit. You'll notice that there are some of the similarities to what we've already talked about, as well as a few new things popping in as well. But what I plan on doing in this section is I'm going to go through most of the notes, and then I will post the examples. I will post those probably as just a worked out document, and then I will explain those a little bit in class if we need extra help, but I'm guessing we'll probably be pretty good on most of the examples. So anyway, let's just get to the notes. So the first thing we're going to start with is this principle of superposition. We've actually talked about the principle of superposition before, going back to last year. And the simple definition of the principle of superposition is simply when two or more of really any type of entity are interacting. So we often deal with it when we're talking about two or more waves, right? But it could be any type of, it could be two or more forces, it could be two or more of a variety of different, physical phenomena. So anytime we have multiple things that are interacting at a single point in time or a single point in space, that's what we talk about when we talk about this principle of superposition. So really the consequence that has for waves, as we often know, is it provides us with either constructive or destructive interference. Remember those terms from last year, which were pretty straightforward, right? So constructive interference, destructive interference, right? Constructive interference when the waves add up. So when they add up, and then obviously when they destructively interfere. So when they subtract the amplitudes, right? Something like that. I should make mention here of the fact that the waves themselves are not adding up, but the amplitudes of the string would be adding up at that position. But anyway, so a relatively simple example of this then would be, right, if I want to find out what the superposition is, it says sketch the wave displacement of the diagrams at 1 second, 2 seconds, 3 seconds, 4 seconds. So they're giving us the initial diagram. Notice that this is at 0 seconds. Notice also that the two waves are moving towards one another. So we're just going to draw these diagrams after time has passed, and we're just going to kind of do these snapshots for what's happening from there. So anyway, as I look at this, what I like to do is, again, just kind of look at so they're each moving at 1 meter per second. So after 1 second, the leading edge of this triangle right here should move forward 1 meter, right? Because after 1 second, it's going 1 meter per second. So it should be there. Whereas the leading edge of this rectangle should also be moving forward 1 meter. So that takes it to 3 meters as well. So my next diagram actually should then have the two images here kind of right up next to each other, but not yet overlapping. So at this point, they're not overlapping. They're simply kind of up snug next to each other, right? At 2 seconds, they're going to continue to progress. So my leading edge now for 3 is now over here at 4, whereas my leading edge for the rectangle at 3 is now over here at 2, right? So if I kind of play that by ear, so notice the back end of the triangle would also be at 2. So the rectangle is at 2, but then the triangle is also at 2. So it's going something like that, right? And then I have the rest of the triangle here. And then I have the rest of the rectangle, which would drop down. And by all means, feel free to, at any point, if you want to pause and kind of work ahead and try these on your own, you're certainly welcome to do so, right? But this is what it would look like after 2 seconds. Now, if you wanted to draw the images separately and have kind of your triangle here, maybe as a dotted line, and then just simply superimpose them on top of each other, that would be perfectly fine too. But anyway, we can certainly draw those separately as needed. So then at 3 seconds, we're looking here, right? So at 3 seconds, once again, the triangle's leading edge has now moved one further forward. So the leading edge of the triangle should now be at 5 seconds, whereas the leading edge of the rectangle should be at 1 second. So over here at 1 second, we have the rectangle progressing forward. The back end of the triangle would now be at 4 seconds, correct? So the back end of the triangle at 3 seconds has now moved forward to 4 meters, I should say, on that position. So basically what we're going to end up with here is we're going to end up with most of the rectangle passing through then the picture as we're going forward, right? So the rectangle is now passing here all the way over to 4. And then at that point, we have the triangle, which is now I guess actually going back to 3. Sorry about that. So going back to 3. So here's my triangle. So this would more or less be my image. I'm going to go ahead and get rid of that line. There we go. So that would be the resulting wave for at 3 seconds. So a little bit trickier to find that one, but we can see again that half of the triangle here is still overlapping with the rectangle. So we've got that image as well. Now at 4 seconds, the two will have completely passed through each other, right? So the back end of the triangle will now be at the 5 meter mark, right? Because it's moved forward, excuse me, at the 4 meter mark. I keep referencing the wrong picture. That's what it is. So it will now be at the 4 meter mark. So there's my triangle. And the back edge of the rectangle will now be at 3. So it looks something like that. So again, hopefully this example is pretty easy as you work through it. I know it took a while to go through there, but if you have any questions on something like this, let me know. I can certainly give you other ones, but I think that one's probably pretty straightforward for us. So nothing too crazy on that one. So then, if we look at the next part down there on your diagrams, on your example pages, right? So standing waves, we've talked a lot about standing waves in the past, right? The features of a standing wave to be comfortable with are, of course, the antinodes and the nodes. The nodes represent areas where we have destructive interference such that the resulting amplitude is, notice, basically it's 0, right? So it's destructive interference such that the resulting amplitude would be 0. And it is worth noting that at the nodes, the amplitudes would always be 0, right? So those points are not oscillating up and down. Those points would be staying at 0 the entire time. So they don't oscillate up and down, they stay at 0. The points at the antinodes would be oscillating up and down, but the antinodes are simply distinguished by the points that cover the most distance per cycle, right? So they're covering the most distance per cycle as they go. So nodes and antinodes, again, we've seen those before, right? And we'll talk more about the resonance and all the properties that come with that, right? But we definitely need to be able to distinguish nodes and antinodes. Now notice we also tie in intensity, which we just talked about in our last chapter. And notice that the intensity is matching up with the nodes and antinodes. Now it makes sense, right? If the waves are completely canceling out, and I should be careful, if the amplitudes of the waves are canceling out at the nodes, then they do not have any intensity at the nodes, right? Whereas they would have a maximum intensity at the antinodes where the two waves are constructively interfering, right? So the antinodes represent areas where we have constructive interference, right, happening from there. Okay, so we've seen diagrams like this before. Again, hopefully this feels pretty familiar, right? This is something we went back to doing last year. Nothing too overly new or crazy, right? So here's where we get to the new aspect of how we're going to deal with superposition. So again, the idea of superposition is the fact that you have two waves overlapping, right? So we've got two potential waves here that are overlapping that are causing these standing waves. Well, if we think about this, if you send a wave pulse down a string, right? So if I send a wave pulse down a string, I know that when it reaches the end, that wave pulse is eventually going to reflect backwards, right? Now we'll talk about fixed versus free end reflections. But if it's fixed, it would actually, right, bounce back on the other side. But that can still help us figure out where the areas of destructive versus constructive interference would happen. Well, let's simplify the whole scenario a little bit here to see what's actually happening kind of mathematically. Now, again, we just saw the graphical representation. But if we look at what's happening mathematically, here's what we can do. So we can define the displacement function. So notice that this is basically my d is, right, my d of x and t. So this is the exact same function we had so much fun with in the last chapter, right? But notice my displacement function here is representing the displacement function of a wave moving to the right. So this function would be representing d sub r of this particle here as it's going to the right. Well, d sub l is basically the same thing. The only difference is the negative becomes a positive. And the reason for that is because the direction has changed. So because the direction of the angular velocity and the direction of the linear velocity matter, when it's returning to the left, we actually are going to define that as being a positive value. Now, I don't want you to stress about too much of the why behind that. I don't want us to worry a ton about that. But I do want you to realize that simply, right, if we're keeping this plain and simple, when the direction reverses, right, since velocity or angular velocity, since they are both vectors and the direction matters, the direction there changes as we change their direction. So this would represent the wave function as it's moving back. So if I wanted to find the superposition at any random point, I would simply take these two functions, right, which again are both individually almost exactly like the functions we just dealt with in the last chapter, and I would simply take those two functions and add them together, right? So here I have this wonderful mess where I've taken each of those two functions and I've added together, right? So I've got those two and I've added them up. Well, we can actually take advantage of a few trig properties that I know we all remember and love these trig properties, right? But it allows us to actually take this and clean this up a little bit more and see what happens. Okay, so I've currently got this function of a sine kx minus omega t plus a sine kx plus omega t, right? But I'm going to use each of those sine functions individually, and I'm going to break them up using this trig property. So the first thing I'm actually going to do is, since both of my terms up here above, since both of my terms have an amplitude out front, I'm going to go ahead and factor the amplitude out front such that I have this as my function. So this is what I'm looking at right now. So I'm going to kind of just know that my amplitude is out front. I'm going to pull it out front, but I'm going to forget about it for right now. So now what I'm going to do is I'm going to take sine of kx minus omega t, and I'm going to make that fit this pattern down here. So in other words, I'm going to make kx my alpha, and I'm going to make omega times t my beta, right? And if you hear some noises in the background, it's just Max getting some water, so don't freak out by that. Right? But anyway, so I've got alpha and I've got my beta, which I'm defining as that. So then sine of kx minus omega t, if I just take that first part, well, if I follow this rule, that would break up as sine of kx times cosine of omega t, because here's my alpha, here's my beta. And then since it's a minus, it would be minus cosine of kx times sine of omega t. So notice we took this single sine function and we expanded it, which I know makes it look worse at first, but we expanded it, right, into those two separate functions. Okay, so this is only the first half of what I'm going to do. Now I'm going to do it again, except I'm going to do it again for my other function, right? So I'm going to do sine of kx plus omega t, and then I'm going to break that up as well. So this would break into, if I'm using this again, because I'm using the plus, I'm going to use the plus. So sine of kx, and then cosine of omega t. Notice the first part doesn't change. The only difference is instead of minus, I'm now doing plus cosine of kx, sine of omega t. So these would be my two functions separately as I break those up. Now notice with these two functions within that parentheses there, right, we are adding them together. So in other words, to clean this function up, because right now it looks like all we did was make this worse, but to clean it up, I'm going to take each of these two functions and I'm simply going to add them together. Well, if you notice, the second term in each of them are the exact same thing, except they are opposite signs. So if I take these two functions and I add them up, that cancels out. This term is the exact same as this one, so I end up with 2 sine of kx cosine of omega t. Now don't forget that what did I factor out at the very beginning? I still have extra amplitude, which I need to bring in. So in other words, all of this boils down to this wonderful disaster that is d sub x of t, or d of x of t, I should say, right? X of x comma t. So this function, which represents the resulting superposition for the two functions, this displacement function here representing dr plus dl, ends up being 2. I'm going to bring the a into my function as well, so 2a sine of kx cosine of omega t. So here is my resulting function. This represents the superposition of a wave as it is bouncing down and back. So this represents the superposition for a wave function that is interfering with itself. So superposition of a wave interfering with a wave of the same frequency. So with itself or any other wave of the same frequency and wavelength and all of that fun stuff. So wave of same frequency. Okay. So we do all of that mess. Now, again, you don't necessarily need to be able to prove this whole fun stuff every single time. It is nice to see where that comes from, but this is ultimately the function that we get. So when we look at what this all tells us, right, if we kind of summarize this all together,